So yesterday we were talking about sequences. So we got a few definitions. The last thing we talked about was monotonic sequence. Basically, a monotonic sequence is a sequence where the change from one term to the next is always in the same direction. So it's increasing or it's decreasing, and it's also usually one sign, positive, mostly positive. The next special kind of sequence is what's called a bounded sequence. And as the name implies, it's a sequence that has a finite value for a sub n as n approaches infinity. So an unbounded sequence would just be, so I'm going to give you an example of an unbounded one. So if I said the sequence was defined by the nth term being just n, so this sequence would be, if I drew the picture of it, it's basically just a straight line. So the nth term is just n, and so it would be something like this. So this would be defined as a monotonic sequence because it's increasing in the same direction consistently. So this is non-bounded, not bounded, because, or unbounded, I guess you could call it, because if you take the limit of a sub n as n goes to infinity, we say the limit of this diverges. So an unbounded sequence, the limit of the nth term as n goes to infinity would become infinity, or we would say it diverges. Whereas something like a sub n is 1 over n, this is monotonic as well, but it's also bounded, because if we plot that sequence as a function of n, it's going to look something like this. It's going to be just a half, a third, a quarter, a fifth, a sixth, so forth. And so if you take the limit of a sub n as n goes to infinity, in this case it's 0. It doesn't have to be 0, it just has to be some value. So it could be 1, it could be anything. It just cannot be infinity. So that's what a bounded sequence is. Now the sequences that ultimately become series that are of any consequence have the nth term go to 0. If the nth term doesn't go to 0, then when you add up the terms in the sequence, which is a series, it'll end up being infinite. It'll diverge, and it doesn't really give us anything useful. So all the useful ones are, well, they're not necessarily monotonic, but they're bounded, and the limit is going to be 0. Okay, so that's what bounded means. Yes?
So all, or at least most bounded sequences will have converging limits?
You would have, yes. Not all of them would have. Yeah, so they would all converge to something, not necessarily 0, but to, so bounded ones just have to go to some limit to some value, so they converge. But the useful series, the nth term always goes to 0. But that's a special case of a bounded sequence. Okay, now we're going to talk about factorials, which you probably have had before. And the reason we're talking about that is because when we get later in the chapter and we talk about infinite series, a lot of them involve factorial in the formulas. And also, even now, if we had a sequence and we wanted to include factorial in the definition of the sequence, then we need to know what it means. So if you take a number n, any number n, and you do the factorial of it, that's just n times n minus 1 times n minus 2 times dot 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 down to 2 times 1. So it's just the number, starting with the number that we're finding the factorial of, just decreasing it by 1 until you get down to 1 and multiply all those numbers together. So 5 factorial is 5 times 4 times 3 times 2 times 1. 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, so that's factorials. And if you remember yesterday, well, let me just zoom back here for a second. When I introduced where we were going, the definition of the sine and the cosine involved factorials, so it's important. Now another thing, if you take the ratio of factorials, this is more important if you do probability, or not probability, but permutations and combinations. But let's say you have 5 factorial divided by 3 factorial. So one way of simplifying that would be just to write them out as their full definition. I mean, factorials are just shorthand for, it's kind of like exponents. I mean, 2 to the 5th power is short for 2 times 2 times 2 times 2 times 2. In the case of factorials, it's that representation. Somebody might be tempted to say 5 factorial divided by 3 factorial is 2 factorial, or 5/3 factorial, and both of those would be wrong. For one thing, factorials are always integers, and secondly is it doesn't work that way. So you can see if I write out the factorials in their definitions that these cancel out with those, and you just get 5 times 4, which is 20. So 5 factorial divided by 3 factorial is 20. Another way of looking at this, and the easier way, is if you have something, say 7 factorial over 4 factorial, instead of writing it out completely, you write out the larger factorial with the terms, and then when you get down to the number that represents the factorial in the denominator, you just write 4 factorial. So we can always write a factorial as the product of integers, the upper integers, and go down as far as we want to, and then put the remaining number factorial. So 4 factorial is 4 times 3 times 2 times 1, and so the numerators, they're equivalent to each other. And at that point, you can cancel out the 4 factorial, so it just saves you having to write out, this cancels out with that. And that's the only time you can do anything with factorials besides just write it out in its full form. If you have the any factorial over the same factorial, it's the same term, so it equals 1. So in that case, that would be 210. So the point of this is just that you can simplify the ratio of factorials. They're not usually a factorial. They are part of the factorial, usually the larger numbers. Okay, so here's some examples of what the problem assignments are for section 1. So one is just taking a definition for a sequence and writing out the sequence for a specified number of terms. So it says write out the first 5 terms of the sequence, and you can kind of do this just like you would do setting up a table to look at the values of a function. So I'm just going to create a table where the first column is n and the second column is a sub n. So we're going to start, didn't say where to start, but we could start at 0 or 1. Let's start at 0. We'll do all the way up to 5, so that's really the first 6 terms. But all you do is just stick in the value of n into the equation. So this would be 0. If you put 1 in here, you'll have 2 divided by 4. So you'll have 2/4, which is 1/2. If you put 2 in there, you'll have 4 over 5, which you can't simplify. If you plug 3 in, you'll have 6 over 6, which is 1. Put 4, you'll have 8 over 7, right? 8 over 7, which is, that's as far as you can simplify it. And then you'll have 10 divided by 8, which is 5/4. they don't ask you in the particular problem, what do you think the limit of a sub n as n goes to infinity is? Just think of it if it was 2x over x plus 3. Just take the ratio. Yeah, go ahead. Well, think about it as ratio. It's a polynomial. It's a rational function. If I were to say, what's the limit of 2x over x plus 3 as x goes to infinity? It's a rational function. So you look at the order of the exponents, which are both 1. Yeah, so Daniel's got the answer. It's 2. Okay, so it's the ratio of the leading coefficients. So the answer is 2. So this would be, if we would say, is it bounded? Yes. Is it monotonic? Yes. It's bounded because the limit as n goes to infinity of the sequence has a limit, a finite limit. And it's monotonic because you can see how it's slowly getting larger, and it's going to keep getting larger till it approaches 2. Okay. Next one. Write the first 5 terms of that. Why don't you guys try that one? Just set up a table again, plug it in there. This is, let's see, this looks like there's a parentheses missing, so I think it goes right there. So it's n times n plus 1 divided by 2. Does that actually end up with an even number? Let's see. And do start from n equals 1, because you can't define. It's not defined when n equals 0. So you make up a table here. 1, 2, 3, 4, 5. I'll do the first one for you. So you'll have negative 1 to the 1 times 1 plus 1, whole thing divided by 2, over n squared. So that's 2 times 1 divided by 2, so that's negative 1 to the first power divided by 1 squared, which is negative 1. Negative 1 to the first power is negative 1. So then the next term you'll have it to negative 1 to the 2 times 2 plus 1 divided by 2 over 2 squared. And then you plug in 3. I need to make a little more space to my calculations here. So. Let you do the last two. So you see the first two terms are negative. If I did it right, 2 divided by 2 is 1. 3 times 2 is 6, divided by 2 is 3. So because the first two terms have negative or odd exponents in front of negative 1, you get negative signs. But then when you get to 3, you get 3 times 4, which is 12. 12 divided by 2 is 6, which is even. So you end up with positive 1 instead of negative 1. I don't know what happens if it automatically becomes positive after this or not. Probably, but I'm not sure. Huh. Cool, interesting. So I don't remember doing that one before. Anyway, it's kind of interesting because the first two terms are negative, the second two terms are positive, the last term is negative because you end up with 5 times 6, which is 30. 30 divided by 2 is 15, which is odd, so you get a negative sign. Okay, so anyway, that's basically what you do. It's just to show you different kinds of arrangements for sequences. The next group of problems you have to just recognize the pattern. You don't have to come up with the equation. So you look at that and you think, okay, what is the pattern? And a lot of times, if you have a whole number for the first term, you might want to write it as 1 over 1. Okay. So one thing you can see is that it's alternating signs. You can see the first term is 1, and then the second term, the numerator is a multiple of is first term times 3, and the next term is the second term times 3. So you're multiplying each term by 3 in the numerator, and you're multiplying each subsequent term by 2 in the denominator. So by just kind of looking for patterns relative to kind of like geometric sequences or arithmetic sequences. So the next two apparent terms would be positive because it goes positive, negative, so it's positive, and we multiply that by 3, so that's 81 multiply that by 2, which is 16, and the next one would be negative 273 divided by 32. Now, how would you do that? They don't ask for it, but if you were trying to figure out how to do this, you'd have negative 1, and let's say this is the first term. So you'd have, and this, we'll say that's the second term. So these are the ends. So then you would have to the n plus 1, because the first term is positive. So if n is 1, I need 1 plus 1, which is 2, to make that even. And then when I have the third term, or the second term, I'll have 2 plus 1, which is 3. 3, negative 1 cubed is negative. Okay. And then you'd have you'd have 3 to in the numerator, you'd have 3 to the n, and then in the denominator, you have 2 to the n. So that would be the equation for that particular sequence. This term is used to alternate the sign. You can see, actually that wouldn't work. It would be to the n minus 1 power, right? So, because 3 to the 0 power would be 1, and 2 to the 0 power would be 1, so that works out for the first term. I could do n minus, I couldn't do n minus 1 because that wouldn't work out. But anyway, that's kind of that's the actual equation. And I think you have to do that for some of the later problems. Okay, there's the simplification of factorials. So the way we would do this is, I don't have a specific value for the factorial, but you can rewrite any factorial as such. So it would be n plus 1 times n factorial. So if I had, if I had n plus 2, I could write that as n plus 2 times n plus 1 times n factorial. Or I could write it as n plus 2 times n plus 1 times n minus 1 factorial. So you can do the same kind of things for factorials that don't actually have numbers, and you can see how that the top expression, I would go ahead and simplify it further, so I can cancel out the factorials, the n factorials. So this is equivalent to just n plus 1. So the same kind of thing here is you want to get to a point where you have the same factorial so that you can cancel it out. So you can see what I probably would do is I'd take this and I would rewrite the denominator as n 2n plus 1 times 2n times 2n minus 1 factorial. So all I'm doing when you take a factorial is you take the initial number and subtract 1, which gives you that. And then you subtract 1 more, that gives you the next term in the factorial. And then I've gone far enough where I can match up the factorials in the numerator and the denominator, and there at that point I can cancel out the common factorials. So this cancels out with that, and you're left with 1 over 2n plus 1 times n, 2n. I guess you can multiply that out a little further if you wanted to. Doesn't really matter. Okay, so that's another thing. So you do a few little factorial problems, and then find the limit of the sequence. And the key thing here is that the same rules that we would have used for functions apply for sequences. The only difference between a sequence and a function is that the sequence is only evaluated at integer values greater than 0. So if I want to know what the limit of this sequence is, so the limit as n goes to infinity of a sub n, which is the limit as n goes to infinity of 5n over the square root of n squared plus 4, that would be the same value as the limit as x goes to infinity of 5x divided by the square root of x squared plus 4. And probably the easiest way to think about this is just, again, if you if you have multiple terms in either the numerator or the denominator, when you let x become large or n become large, the other terms become insignificant. So I can pretty much ignore that term when it comes to finding the limit. So I'm left with 5x over the square root of x squared, and so then I can just take the square root of x squared, which would give me x. So we could say when x is large, the limit as x goes to infinity of 5x divided by the square root of x squared plus 4 is approximately equal to the limit as x goes to infinity of just 5x over the square root of x squared, which is equal to 5. Okay, because the denominator would just become x. So the x's cancel out, and ultimately it's just 5. So because this is 5, the answer to the original question is 5 as well. You're not going to write out 100 terms or something like that and see where it goes. You're just going to treat it as a function in terms of using the procedure. So the same thing. Well, same thing here. When it asks for determine the convergence, it's basically saying what is the limit as n goes to infinity. If you get a number, then it converges. If it's unbounded, then it diverges. So that's what the terminology means there. So again, it's a ratio of leading coefficients because you have an n squared in the numerator and an n squared in the denominator. So when they ask you to solve this question, all you're basically doing again is saying, oh, you want me to do this. If you want questions about convergence, you want me to take the limit of the sequence as n goes to infinity. And so the answer is 3/2. And so therefore, we have to say one additional thing. Therefore, the sequence converges. Let me just give you an example, one which diverges. So if they ask the same question for a sub n is equal to n squared divided by n plus 1, what I would do is I'd take the limit as n goes to infinity of n squared over n plus 1, and that would end up being infinity. And therefore you'd say, therefore, the sequence diverges. Okay, so that's what they're looking for. So the another example is this. So again, you take the limit of that as n goes to infinity. So what is the, in that case, it's not quite obvious what's going on, so it might be worth writing out a few terms. So we'll start at n equals 1. Because it's not, if it was just negative 1 to the n over n squared, then it would be kind of obvious. It would be an alternating, it would alternate between negative and positive, and it would get smaller, so it would kind of go like this. Boom, 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 boom. The question is, how does this extra 1 affect what's going on? So we're just going to, so this is n, a sub n, start at 1. We'll do 5 terms, probably good. So we'll get 1 plus negative 1 to the first power divided by 1 squared. So that's negative 1 squared is 1. Negative 1 to the first power is negative 1. So you get 0 over 1 squared, which is 0. Okay, let's try 2. So you get 1 plus negative 1 squared divided by 2 squared. So there you'd have 1 plus 1, which is 2, divided by 2 squared, which is 4. So you get 1/2. And then when n equals 3, you'll get 1 plus negative 1 cubed over 3 squared, which is going to be negative 1 to the third power is negative 1, so you get 1 minus 1, which is 0, 0 over 9, which is 0. And the fourth term is 1 plus negative 1 to the fourth divided by 4 squared. So you would get 1 plus 1, since this is the even power, so you get 2 over 16, which is 1/8. So really, that extra term doesn't affect the convergence. Even though this thing keeps going to 0 every other term, the other term, the one that actually has a finite value, is also going to approach 0. So it's a little weird kind of behaving sequence, but it's still going to approach 0, just as we thought it might anyway. So we would be able to, from just looking at the function, seeing how the denominator gets smaller and smaller in every other term, we can conclude that the limit as n goes to infinity of 1 plus negative 1 to the n over n squared is equal to 0. Therefore, the sequence converges because it's something other than infinity. See how many more problems I got here. I got, okay, 4 more. Okay, so let's see what this one is. So again, we're asking what is the limit of a sub n as n goes to infinity. Oh, I gave the answer away. Okay, so why is it 0? How do I know it goes to 0? Yeah, that's right. Yeah. So what you're basically an easier way to say what if you can rewrite the original thing as 3/4 to the n. So because the base of that exponential function is less than 1, any number that's less than 1 raised to the infinite power goes to 0. You know, it's going to, when you multiply it by itself, you get 9/16, and then you multiply it by again, the denominator is going to grow much faster than the numerator, and that happens anytime you have a fraction that's between 0 and 1. So that's why you know that's the case. What you can, kind of a general comment is, if a is between 0 and 1, then the limit of a to the n as n goes to infinity equals 0. You can try that on your calculator. You know, if you take 3/4 and you raise it to the millionth power, you'll get essentially 0. And you can pick any number to do that with. So if you do that, just you get 0. Okay, 3/4 to the millionth power is 0, according to the accuracy of the calculator. It's not exactly 0, but it's close enough to 0. By the way, I did look at the proof of L'Hopital's rule, and I was working on that. But you've got to prove another thing first to be able to prove L'Hopital's rule. It's in the appendix of the book if anybody's interested, but I will present that. I started on it and I don't have time to finish all this. So there's another theorem called the extended mean value theorem, and so you got to prove that first. And then you can use the extended mean value theorem to prove L'Hopital's rule. I still haven't figured out why it works for indeterminate stuff, but it doesn't work for determinate stuff.
I think it's because around when you evaluate a function at 0, the value of that function for some small change in like dx would also be equal to the value that the derivative of that times a small change.
Okay.
But if you actually have a value that's not 0, it's going to kind of add a number to another number and then divide those two numbers.
Yeah, because I think, we talked about there are various indeterminate forms, but in reality they're all the same. I mean, even if you have an infinity divided by infinity, you can take the reciprocal of that and you get 0 divided by 0, or 0 times infinity is all of them end up being 0 divided by 0 essentially. I think that's probably the case, even though you think they're not. They're not just 0 divided by 0, but they are ultimately all 0 divided by 0. So what you're saying makes sense as far as that situation. Oh, so therefore, A sub n converges. Okay, this one, what you would do is you would simplify this and then look at the resultant simplified expression. So we could rewrite the denominator as n times n minus 1 times n minus 2 factorial. So, and I did that again so that I could get the denominator to include this factorial, so then I can cancel them out. And so you'd have 1 over n squared minus n, this times that. So I went ahead and multiplied it. And that one obviously is going to be 0. So the limit as n goes to infinity of 1 over n squared minus n equals 0. Therefore, a sub n converges again. Okay, so both of these, initially they're not obvious. The first one you can rewrite as a fraction, and then think about any time you take a fraction to a very large power, it goes to 0. And over here we simplified a factorial expression. Now, the last two problems are coming up with the equation. So it says write an expression for the nth term. So again, probably it might be good to write this as negative 1 over 1 and 2 over 1. So we do have this alternating nature to it. So that means you got negative 1 to some power. And the denominator looks like it's some power of 2, right? 2 to the n power, or n something power. But you know, that would work out okay if I was looking here, but I've got this extra term. So how the heck do I make that work out? Well, if I multiply the whole thing times 2, maybe. And if I start with n equals, let's see, I could start with n equals 0. So let's just think about that. If I try this expression with n equals 0, I'll get, and let's just put n, we'll just put n for right now. Somewhat kind of a puzzle game here. So if I use this and I let n equal 0, does that work out right for the first term? 2 to the 0 power. 2 to the 0 power is 1. Negative 1 to the 0 power is 1. So that works out. That is actually, so negative 1 to the 0 is 1. 2 to the 0 is 1. So the answer is 2. Okay, let's try n equals 1. See how that works. So if I try n equals 1, I get 2 times negative 1 to the first power divided by 2 to the first power. So that's 2, negative 1 to the first power is negative 1, divided by 2 to the first power, that becomes negative 1. Okay, hey, that's pretty good so far. I might have gotten lucky. Now if we try n equals 3, I'm going to start feel confident. N equals 2, I'm going to feel pretty confident. So 2 times negative 1 squared divided by 2 to the first, 2 to the second power. So what do I get there? I'll get 2, negative 1 squared is positive 1, 2 squared is 4, and I get a half. Okay. So it looks like that's the right expression. I got kind of lucky. I don't ask you to do this on the test, so don't worry. But I want you to at least try it out. But that was the thought process there was, okay, I know that the denominator has to be 2 to some power because I've got 2, 4, 8, so forth. So that makes sense. I didn't know exactly how that was going to work out. I knew that you had to have negative 1 raised to some power because we had the alternating signs. Again, I wasn't sure if it was n plus 1, n minus 1. And then I thought about the first term a lot of times is 1 unless you do something special to it. So I said, maybe I just need to multiply by 2. And you might say, well, could I simplify that and make it 2 to the because I've got 2 to the first power in the numerator and 2 to the nth power. So I think you could, but it just seems easier to see under those circumstances. So anyway, give it a try. And then this one here. So let's see if you go ahead and see if you can come up with the expression from a sub n. And you have to decide whether you want to start. In this case, I let n start at 0. So usually you have to specify that, or you. So it's all the same. Yeah, go ahead.
Should you start usually with n equals 1 or n equals 0?
I mean, in this case, it doesn't really matter. I think if you don't do it, you're supposed to assume 0. But it doesn't. If you want to start with 1, that's fine. So, because it's all the same sign, you're probably not going to need -1 raised to a power. In this case, I'd probably just start with 1, just because it's an easier expression. So that's it. I mean, you can see how each number increments by 1, and so you look at the first expression. If you have 1 in the numerator, that's n. 2 is n plus 1, 3 is n plus 2, and so that seems like, just by looking at the first term, that seems like a reasonable concept. And then if you try n equals 2, it just falls into place. So that would be it. Okay, so let me give you the homework assignment for this section. If there's any numbers you don't know what it says, let me So what we'll do next time is we will talk about series, which are basically sequences where you add the terms together. And if you go back to, yes, Seth. Pardon me? Yes. So what we'll do is talk about series, and then we'll talk a lot about convergence of series. There's about 10 different tests for looking at the convergence of series, and we'll look at all 10 of them. So that's the. So breakfast is this morning for Governor's School. At least that's what they said. We'll find out.